welcome back. So, now also you consider for which one it is, for 5 you can consider, you see A B is equal to A C union of C B. Now, what you can do is that you consider a partition for this. So, you consider as A C and you do not the partition here for C B. So, you show that you take, then obviously given you have to be little careful, and I would urge you to write down the proof. So, P of A C union of P of C B, this is equal to you are going to get P of A B. And now, in order to get P of A B, what we need is that we need to make the particular choice of the partition. We can always get a partition make a finer partition. Suppose given a P of A B, we get a partition P prime, which is going to contain P and of A B such that C belongs to P prime. That means, what I am saying is that suppose I have a C here, A and B here. Suppose my P is this is x 1, this is x 2, this is x 3, this is x 4, this is x 5, x 6, like this. Now, what this is my P, and the C is not, C does not belongs to P. So, what I am going to do is that I will take the partition A P prime, I am going to denote it as A, which is equal to x naught, which is less than x 1, less than x 2, in this particular thing less than x 3, less than C, less than x 4, less than x 5, like this, which is equal to B. Now, as you can see that this P prime is containing all, the P prime is definitely going to contain all the points of P. So, P prime is contained in P. Now, if you look at the norm of P prime, this is going to be the maximum of the individual thing. So, now if the maximum is attained anywhere here, then that is fine, but if the maximum is between x 3, so this is always lesser equal to maximum of P. So, now if norm P goes to 0, then norm of P prime will also go to 0. So, keeping that in mind, we can always make a partition of A B. If you give me a partition, I can get a refinement of that partition and make the things work. However, so this is going to be true, and also if you look at f of x g of x, your choice of C k, f of C k is lesser equal to g of C k. So, you can get that choice of the partition. Okay, so far so good. So, this is the sketch of the proof. Now, once you have this algebra of the Riemann integration, what one can do is that one can evaluate, let us say a to 0 to 2, 3 x cube minus 7 by 2 x square plus x plus 1. So, this is definitely this we have computed 3 x cube integration, we have computed x square integration x and the constant function 1. So, this is an integrable function. So, in particular any polynomial on a closed bounded interval is going to be, it is a continuous function, but it is going to be integrable. And here what we have seen is that this is from alpha times f of x. So, this is 0 to 2 of x cube minus 7 by 2 integral 0 to 2 of x square plus 0 to 2 of x plus 0 to 2 of 1 dx. So, now this what we have seen is that this is b to the power 4 minus a to the power 4 divided by 4. So, this is 2 to the power 4 by 4 minus 7 by 2 into this is b q minus a q divided by 3. So, this is 2 to the power 3 divided by 3 and this is 2 square by 2 and then this is 2. So, we can simplify and get the. So, one can, because with f of x is less or equal to g of x, I mean even if we sometimes we may not be able to compute the Riemann integration, but we can always say that there is some upper bound or lower bound for this integral, even though we are not able to compute it precisely, but still we can get certain inequality involving that integration. So, for example, so that the value of sin x dx cannot be equal to 2. Okay, so, to find this inequality, I do not have to compute this integral, because what this question is asking us not to compute the integral. It is saying that it is asking much less than the precise value of the integral. Suppose if we can show that this integral is strictly less than 2 or strictly greater than 2, then we are done, it cannot take the value 2. So, let us try to do that. What is square root of 1 plus sin x? Let me be little careful about it. Yeah, so between 1 to 2 sin is always going to be positive. So, this is definitely less or equal to square root of 2. Therefore, the integral 1 to 2 square root of 1 plus sin x dx, this is less or equal to 1 to 2 square root of 2 dx, which is equal to square root of 2 into b minus of a is 1. So, as you can see that this integral is always less or equal to square root of 2. So, it cannot go beyond square root of 2. Therefore, it can never be equal to 2. So, which is strictly less than 2. That is what we wanted to show. Similarly, let us see another example of this nature. We have seen that as an application, we have seen that cos x is greater or equal to 1 minus x square by 2 as an application of mean value theorem. So, integral over 0 to 1 cos x dx, which is greater or equal to integral of 0 to 1 minus of x square by 2 dx, and this we have computed. This is integral 0 to 1 dx minus 0 to 1 x square by 2 dx. So, this is equal to 1 minus 1 by 6, which is equal to 5 by 6. So, therefore, integral 0 to 1 cos x, I mean, which we may not know the precise value of cos 1 as we had seen it earlier. However, what we can always say that the integral is going to be greater or equal to 5 over 6. Okay. So, we will see more application of the Riemann integration, but still we I mean we have defined the Riemann integration in terms of the area, that is the area under the curve. So, let us see one example of this. Suppose I have a curve like this and I want to compute the area. So, I can compute the area like this. Now, I am going to compute the area of this and then I will add it up. My area is going to be. So, then what is how I am going to compute this? So, now suppose this is an let us say 0 to b and here is a. So, first I will compute the area of this, then I will find the integration of this and this is negative. So, I will add it up to get the area. So, for example, you can see this, find area of the region bounded by a is equal to 2 minus of x square and 0 lesser equal to x lesser equal to 2. So, we will spend more time on the area at a later stage. So, this let us see quickly how we are going to do this. Now, suppose if I am taking the 2 minus of x square, if this is root 2, then this curve is going to be like this and at 2 this is going to be minus of 2. This is root 2 and this is 2. So, what we need to find is this is 2 and we need to find first this area and then this area and we need to add it up, because this is the total area. So, we need to add it up. So, now in this case, so basically for this area what we have 0 to square root of 2, this is 2 minus x square dx. So, we know how to compute the area of 2 and we also know how to compute the area of x square. So, this is going to be 2, if you compute this, then this is basically which is going to come out to be 4 root 2 by 3. Now, if you compute this, then this integral from root 2 to 2 2 minus of x square dx, this is going to be equal to 4 by 3 if 1 minus square root of 2. Now, so the total area, so the area is going to be 4 by root 2 by 3 plus, because this is a negative number. So, what we need to do the area, which means we are doing that plus 4 by 3 square root of 2 minus of 1. So, this is equal to 4 by 3 into 2 square root of 2 minus of 1. Okay. So, this is how we calculate the area. So, next what we have not addressed yet is that why the integration the way we are defining, why that matches with the integration what we have studied in class 12. Okay. So, towards seeing that our definition of integration what we had learned before and now. So, towards that let us observe some nice thing about integration. Let us assume that f is a continuous function, let f from a b to r be continuous. Okay, and you take your x k minus of x k minus of 1 by n, a partition P which is equal to b minus of a by n, k is equal to 1 to n. This is the partition what I am taking. And then you take C k belongs to x k x minus of 1 x k. Now, f is a continuous function. So, we can talk of f of C 1, now f of C 2, now f of C n. Now, I divided it by n. So, this is equal to 1 by n summation over f of C k, k from 1 to n. This is what it is. So, which is equal to 1 by n summation over, rather I will put it as 1 by b minus of a into b minus of a divided by n and f of C k. This actually is k equal to 1 to n f of C k, and then this is b minus x k minus of x, oh I am sorry, x k minus of 1, you take it to be b minus of a, and then 1 by b minus of a will sit outside. So, this is nothing but 1 by b minus of a, this Riemann sum corresponding to this choice of C k and f. So, as norm p goes to 0, we know that this one goes to the integration. So, this is the integration. So, therefore, as you can see, this integration is essentially we can view this as an average. So, this what makes us to define, if f is Riemann integrable, then define average of f, this is equal to 1 by b minus of a to b f of x dx. Now, natural question is that does this average, does there exist a C between a and b such that f of c is going to be the average at some point, I mean is it f is going to attain its average. So, that is what is our next theorem, is that if f from a b to r continuous, then there exists a C belongs to a b such that f of c is equal to 1 by b minus of a integral a to b f of t dt. This is called the mean value theorem for the Riemann integration. The proof is not very hard, as you can see that f is a continuous function on closed interval a b, it is bounded, it is going to attain its minimum and it is going to attain its maximum. So, now and also intermediate value theorem says that any number between the minimum and maximum of f is going to attain it. So, from this minimum of f, this is lesser equal to 1 by b minus of a integral of a to b f t dt, because f t is greater or equal to minimum of a, and then the b minus of a and b minus of a gets cancelled, which is less or equal to maximum of f. Now, this is a number which is going to be, which is in between minimum and maximum of a continuous function. So, by intermediate value theorem, because f is continuous, there is a c belongs to a b, because whatever the minimum is attained and where the maximum is attained. So, such that f of c is equal to 1 by b minus of a to b f t dt. So, this is what is the mean value theorem. So, one of the very easy application is that one can see that f continuous on a b, and a is not, of course, a is not equal to b, and if integral a to b f of x dx is equal to 0, then there exists a c, there is a c such that f of c is equal to 0. That means, if the integration of a continuous function is 0, then at least at one point f will take the value 0, if it is a continuous function. So, therefore, this is just an application of the mean value theorem what we have done, because there is a c such that f of c is equal to 1 by b minus of a integral a to b f of x dx. By previous theorem, there is a c such that, and which is, this is 0. So, this is equal to 0. So, which means, if the integral of a continuous function is 0 on an interval, then there has to be one point at least in which f is going to take the value 0. So, let us stop it here today, and in the next lecture we will use this and to see that how the differentiation and integrations are related the way we have defined our integration. Thank you.